Okay, so the next type of mean comparison test we're going to speak about is called the paired t-test. So the paired t-test is a little bit different than the group comparison t-test, where you're comparing two groups. You're actually looking at paired observations. So just to start, this is a little image I grabbed from the web from another stat book, and you can see that they've got kind of the systolic blood pressures down here. You can see for the pre-treatment blood pressure, it's about 145. After they did the treatment with some drug maybe, or some intervention, maybe running or exercising over time, this is the post-treatment. You can see that the systolic blood pressure lowered to maybe 136, 137. So the question that those maybe study authors or investigators would want to know is this a statistically significant difference going from this peak to this peak for the average? Because again, we're dealing with the t-test, and t-tests deal with the averages, and they also assume a nice normal distribution shape, depending upon the degrees of freedom, how close this shape matches the perfect bell curve for a normal distribution. So anyways, they want to know, is this mean significantly different than this mean? And these are for individual observations on maybe individual persons over a period of time where they may have hundreds or thousands of people in a study. So you can see that they have 150 observations here for this, peak. They have 165 observations for that peak. So there's a lot of people in these bends. So it's a pretty large sample in this little group here. So how do you tell whether or not the pre-treatment and the post-treatment groups are different? You could do that group comparison test comparing two groups like we did before, but that doesn't take into account that intra-sample variability, that kind of those dependent variables where these are the same people, the same observations, or the same samples. So the best option for when you've got data organized in pairs where they kind of come from the same method or the same time period is to use the paired t-test. So we've kind of discussed this example here a little bit. So comparing the post-treatment group versus the pre-treatment group, where we've got data on individuals for both. It'll make more sense here as I show you the spreadsheet of what an example like that may look like. So when should we use a paired t-test? Well, the paired t-test should be used when data are collected as paired observations. So we kind of collect the information at the same point in time or on the same day. Or maybe we collect the observations on the same individual before treatment and then after treatment. The data are paired around something. So treatment group A versus, the same person, maybe post-treatment, or you might have a patient matched up with another patient. You may have different types of treatments, so I wouldn't worry too much about those. But you will see in environmental health a lot, and like industrial hygiene, maybe comparisons of air quality measured by 1 meter versus a newer, better technology, and they're trying to validate method B versus method A. So they may collect paired observations of air quality using maybe a NIOSH or EPA approved method to compare it against a new method that hasn't yet been approved, to see whether or not they should push for approval for method B. In my case, I do a lot of work with water quality, and for example, there have been studies that have kind of done this type of analysis where we might have water quality measured using this thing called the IDEX Alert, where you pour water into a bottle, then you put it into this tray, you seal it, and then you look under a black light and count these dots, and then you match it up with a table, and it will tell you how many E. coli are in your water sample. And then there's the EPA method where you filter water and capture the bacteria on a piece of filter paper, and then you put that paper on this petri dish that's specific for growing E. coli, and the E. coli will have this nice magenta color. So people may have a water sample, a single water sample, and then on that single water sample, they may have Colart E. coli data, and they may also have EPA E. coli method data. So same sample, same water sample, but they do analysis A and analysis B. So I could take that same graph from the beginning, replace it with these results, and say that the average E. coli for this one was 145. The average E. coli for IDEX Colart was 139. And is there a statistically significant difference or not? So we could do that same type of test. A practical example might be like here. So we've got these air quality monitors on top of a building, and maybe the state of Kentucky, they are maintaining air quality monitors in Lexington, and there's one in Richmond. And the Department of Environmental Protection is under financial restraint and under financial constraints, and they need to reduce costs. And one of the proposed suggestions is that we take the Richmond air quality meter offline. So should we do that? Will we lose data? Are we going to miss out on something? So that's a practical question that somebody may have. So you might have a question like, are the Richmond and Lexington air quality monitors producing the same results on average? So you could look at the two groups overall. So for the year, is there a difference? Or for the month, is there a difference? But the best option is to look at the air quality as measured by these instruments on the exact same day and time that they collect their data. Say they collect their data at 10 a.m. every day or at noon every day. So the data are out there. I downloaded them for a month, and I think it was in July of last year. And this was like July 1, this is July 2, this is July 3. And there's data for Richmond, and there's also a way of organizing the data this way. So on day 1 for Richmond, it was 5.4. For Lexington, it was 5.6. For Richmond on day 2, it was 4.6. For Lexington, it was 4.2. On day 3, it was 4.5 for Richmond. On day 3, it was 4.9 for Lexington, and so on. You can see there's some discrepancy here, 7.1 for Richmond versus 5.9 for Lexington. So just a little bit there on letting you see kind of the differences between Richmond and Lexington on this air quality data. And I had 30 days worth of data. So the data can be organized sometimes this way or this way. We'll see which one's best for the paired t-test. So if it's organized this way, kind of these columns where you've got all the Richmond data for 30 rows, and then you go into Lexington data for 30 rows, that doesn't appear to be paired. So when we have the data paired like this, Richmond and Lexington, we're much better off. All right, so when the data are paired this way, we're much better off. And if we're wanting to compare the two, in Stata we can do a simple t-test command, just like we did before. We go to Statistics, Summaries, Tables, and Tests, Classical Tests of Hypotheses, t-test, and then we'll come up with our screen. We would select the paired t-test. If we would need a variable, like the Richmond air quality data being the first row or first column versus the second variable of Lexington, and it's going to be comparing 1 versus 1, 2 versus 2, day 3 versus day 3, all the way for all 30 to see if there's a difference in the means. We would then click OK, and it would end up running the actual test. And it would also give us this command, obviously not that size font, but this is the command, and it's saying t-test Richmond is equal to Lexington. That's the test. And we see we have 30 observations for Richmond, and the mean was 5.43 overall. For Lexington, the mean was 5.4433, and it's asking for the paired t-test. Is there a statistically significant difference between the two, yes or no? This is a two-tailed test, so the p-value is 0.05. And since 0.9055 is way higher than 0.05, we would then conclude that there's no statistically significant difference between the Richmond air monitor and the Lexington air monitor according to the paired t-test. So we have insufficient evidence to conclude a difference exists according to the paired t-test. So we can't use our alternate hypothesis that there is a difference. We have to assume that with the null hypothesis that there is no difference. If you wanted to look at the overall mean of both groups, you could do the two sample rather than the paired test. And, it doesn't really matter. You could still use the same, you can go to the t-test calculator like before, and then just click on whichever one of the two sample tests you want to do. You can do it by group. You can do it by the same way here, where it's same command, t-test Richmond, =, Lexington, and then it'll say unpaired, and then I selected unequal variance. And again, we get a p-value of 0.9759, saying that the overall mean versus the Lexington overall mean are not significantly different. So a little variation. This is looking at the overall. This is unpaired. It's looking at the entire group versus the other entire group. Whereas here, in this particular t-test, this is the paired t-test. It is taking into account those individual pairs of data, day one versus day two, day one, group one versus day one, group two, day two, group one versus day two, group two, day three, Richmond versus day three, Lexington. It's taking that into account in the paired t-test. In the unpaired t-test, it's just looking at the average of Lexington versus the average of Richmond, or the average of Richmond versus the average of Lexington. So it's not taking into account the pairs. It's just looking at the overall group. So the best stat test option for the example is using the paired t-test. We want to use the paired t-test. That's the best one, and it best accounts for those observation-specific days of variability. The data do need to be organized correctly. Observation 1A versus observation 1B, or 2A versus 2B, or Richmond day 1 versus Lexington day 1, Richmond day 2 versus Lexington day 2. If you just choose a bunch of data from Richmond and then lay it up against a bunch of data from Lexington without accounting for the fact whether or not they came from the same day or the same time or whatever, you're not following the rules of the paired t-test. The paired t-test is assuming that you have actual pairs and they're paired around some sort of event. So that concludes the discussion on the paired t-test, and you'll see it used a lot again for like comparing different measurements from instrument 1 versus instrument 2, or comparing new technologies versus old technologies, or comparing a treatment for a person versus their change in that same person, so pre and post treatment. Those are the most common applications. So that concludes this section on the paired t-test.